Oxidation numbers. What are they? How do you calculate them? What on earth do you do with them? This video is going to answer some of those questions. Let's just check some definitions. I like to use the mnemonic oil rig to help me remember what oxidation and reduction means. Oxidation is the loss of electrons, OIL for oil. Reduction is the gain of electrons, RIG. So oil rig helps me remember oxidation is loss of electrons, reduction is gain of electrons.
Let's look at a fairly common half reaction, copper going to copper 2 plus 2 electrons. And we can see there that copper is losing 2 electrons to become copper 2 plus, so it's fairly easy for us to predict that that's an oxidation half reaction. But what do oxidation numbers tell us? Well, if we look at the Cu2 plus ion, notice that the charge of the ion is 2 plus. And that means that the copper atom has lost 2 electrons to get to Cu2 plus. And so the oxidation number then, or the oxidation state, we say is plus 2 because it's lost 2 electrons from its neutral atom. If we have a look at another example, sulfur gaining 2 electrons now to become S2 minus, because it's gained electrons. Remember, reduction is gain, so that's a reduction half reaction. Let's focus on the S2 minus ion. You can see clearly that the charge of that ion is 2 minus, and because it's gained 2 electrons from the neutral atom, the oxidation state, or the oxidation number, we show as minus 2. Notice that when we have the charge, we put the number first, and then the plus or minus second, but when we indicate the oxidation number, we put the minus or the plus first.
And so oxidation numbers are simply the number of electrons that have been added to or removed from a neutral atom. Let's have a look at some of the rules now. There are 5 simple rules that will help you to determine oxidation numbers. We'll go through them one by one.
Rule number 1. Uncombined elements have an oxidation number equal to 0. And so, for example, if we take just pure elemental copper, it's uncombined, hasn't reacted with anything, and so its oxidation number is 0. Another example, chlorine. Notice it's a diatomic molecule, but it hasn't reacted with or combined with another element, and so its oxidation number also is simply 0. Xenon, again, uncombined element, I think you've got it by now, the oxidation number is 0. Second rule, simple monatomic ions, their oxidation number is simply equal to the charge of the ion. And so if we take the Fe2 plus ion, it's a monatomic ion, just Fe, its charge is 2 plus, and therefore its oxidation number is equal to plus 2. Notice again how the order switches around of the number and the symbol. Another example, Br minus, the bromide ion, it has a charge of 1 minus, and so its oxidation number is minus 1. Right, third rule. There are a couple oxidation numbers you just need to remember and learn them off by heart. And this refers to species that are in compound. It's really important, not when they're uncombined as elements. We've already seen that their oxidation number is 0, but when they're in compounds. And so hydrogen, for example, almost always has an oxidation number of plus 1. Oxygen, almost always an oxidation number of minus 2. Fluorine, oxidation number minus 1. So you can learn those off by heart. Fourth rule. In a compound, the sum of the oxidation numbers equals 0. Let's have a look at an example. If we take H2SO4, sulfuric acid, and we focus on the sulfur. What's the oxidation number of the sulfur within that compound? Let's start with hydrogen. The previous rule tells us that hydrogen has an oxidation number of plus 1. I've written that above the hydrogen. But notice it's H2, so there are 2 hydrogens, and so below I'm going to write the combined effect, which would be plus 2, 2 times plus 1. Sulfur we don't know, so we'll just call that X, and there's 1 of them, so that contributes X. Oxygen, we know from our previous rule, has an oxidation number of -2. Notice there are 4 oxygen atoms, and so that gives us a total of -8. And I'm going to put that underneath. And that, when we add it all up, has to equal 0, because our rule tells us that in a compound the sum of the oxidation numbers is equal to 0. And so we can solve for x, which gives us +6. And that means that sulfur in H2SO4 has an oxidation number of +6. And then the last rule, in a polyatomic ion, the sum of the oxidation numbers is equal to the charge of the ion. Let's look at an example, permanganate ion, MnO4-, and focus on the Mn. We don't know what that is, so we'll call it X. There's 1 X, so we put X underneath. Oxygen has an oxidation number of -2. There are 4 of them, so it contributes -8. And when you add that all up together, the rule says that it equals the charge of the ion, and the charge of the ion is -1. So if we solve for x, we get that x equals +7, and that tells us that manganese has an oxidation number of +7. Alright, let's look at some examples. What's the oxidation number of nitrogen in N2O4? That's dinitrogen tetroxide. Let's have a look. We're interested in the nitrogen. We don't know what it is, so let's call it X. There are 2 nitrogen atoms, so it contributes 2X. Oxygen is -2. There are 4 of them, so that's -8. And it has to equal 0 because it's a neutral compound. So 2x is 8, and so x is +4, which tells us that nitrogen has an oxidation number of +4 in dinitrogen tetroxide. Another quick example. What's the oxidation number of chromium in the dichromate ion, Cr2O7 2-? Alright, we're interested in the chromium, so let's call that X. Notice there are 2 chromium atoms there, so it's going to contribute 2x. Oxygen's -2, there's 7 of them, so that's -14, and that has to equal -2 because the charge of the ion is 2-. So 2x is +12, so x is +6, and that tells us that chromium has an oxidation number of +6.
Now that we can assign oxidation numbers, let's have a look at how we use them in redox chemistry. 2 important facts to remember. Firstly, if the oxidation number of a species increases, then it means that that species has been oxidized. And similarly, if the oxidation number of a species decreases or reduces, then that substance has been reduced.
Let's look at this example. It's the one we started with. Copper going to copper 2+ plus 2 electrons. We can see it's losing electrons, so we already know it's going to be oxidation. But let's check using our oxidation numbers. On the left, copper has an oxidation number of 0 because it's an uncombined element. On the right, it has an oxidation number of +2 because its charge is 2+. And we can therefore quite easily see that the oxidation number has increased from 0 up to +2, which tells us that copper is being oxidized. And we knew that from the definition because oxidation is loss. Let's try a couple other examples. Has iron been oxidized or reduced in the following reaction? So we've got FeCl2 plus Cl2 giving us FeCl3. We're going to focus on Fe. On the left, chlorine, remember, is in group 7, and so it'll have a -1 oxidation number. There are 2 of them, so that gives us a total of -2. It's a neutral compound, and so Fe must be +2. On the right-hand side, again chlorine -1, there are 3 of them now, and so it must be -3. So Fe then has to have an oxidation number of +3. So what's happened to Fe? It's gone from +2 up to +3. The oxidation number has increased, and therefore we can conclude that Fe is oxidized. What's been oxidized and what's been reduced in the following reaction? A slightly more complex reaction. The permanganate ion, MnO4- reacting with Fe2+, to give us Mn2+ plus Fe3+, and a few other bits and bobs to balance the reaction. We're going to focus on Mn and Fe. On the left hand side, In MnO4 minus, each oxygen is -2. There are 4 of them, so that gives us -8. The overall charge of the ion is -1, and so Mn must be +7. On the right-hand side, Mn's got a 2+ charge, which means its oxidation number is +2. And so we can see that Mn's gone from +7 to +2. The oxidation number has clearly decreased, and so we can therefore conclude that manganese has been reduced. Let's look at Fe. On the left, it's got a 2+ charge, which means its oxidation number is +2. On the right, a 3+ charge, and so oxidation number is +3. And so for Fe, the oxidation number has increased, and therefore we can conclude that iron has been oxidized. So can you see the oxidation number gives us a nice way to show that Mn has been reduced and Fe has been oxidized.
Alright, so that's oxidation numbers. Go ahead and practice some of the examples that are linked to this video. See if you can become experts at assigning oxidation numbers and then using them to understand your redox chemistry.